Hello everyone. In this video, I'm gonna talk about metaprogramming systems. What's so? So the topic is already to have a question. I will at the class. Okay, that joke was presented to me in our Discord channel for the pregnancy breakfast community, but I think there is a lot to say about what's wrong with C++ metaprogramming. So, just a couple of minutes on about who am I. My name is Andrea Graffiti, and I've been professional programming for more than 40 years now. I started quite young in the early 80s, and I've been programming in many different fields, from started factories off-the-shelf software for doing an office work. Then I went to business software, then medical imaging. Then I worked and for a little bit. I was working on images at the time when I was working in the United States. Then in the last 26 years, I've been in a company that builds industrial robots and mostly working on artificial vision and utilization problems. I started using C++ more than 30 years ago, before it was even a standard. And I'm old. Why I'm saying that I'm old? Because I tend to have this kind of negative view about new things that is very common in old people. I try to compensate for this bias, but just consider this one in a evolution stage. So, what is metaprogramming? Is the first question that I wanted to ask. I want to put a definition. This is my definition, but it's not very far from what you can find on, say, Wikipedia. And in my view, it's code that manipulates code. What does it mean, manipulating? To me, it means that the metaprogramming function is just a regular function, so it's code. It's a programming language where you can write statements and conditional and stuff, but the input or the output is at least partially composed of code. And code, as we know that programs manipulate data, they have input and output. But to manipulate code, it means that you must represent code as data, and to do your manipulation. And your output, that is data, has to be interpreted as the code. And this is one of the ways, in my opinion, in which the mantra code is data, data is truth can be interpreted. There are many other ways, but this is one way to see this phrase. So, clear examples of the code? The first part is the simplest one, but means here we want to write code that generates code. Input can be a number, and the output can be, I don't know, so a code definition of a static table containing data about that number. For example, I get 256 as input, and I want a table of 256 entries for the sine or cosine values to pre-compute those values. This is just one example. And another case is the opposite, where we have an input that is code, and we want to analyze it. And maybe the output is not code at all. For example, we want to introspect in the field and find something, compute something about those fields. I want to get the list of functions called by a specific function or something like that. So input, in this case, code is input, and the output is something else. And in the general case, we have code modification. So we get code as input and we return code as output, maybe after transformation. We did something. We added something, we removed something in the process. One special case, very special case of per generation that is very common, very useful, is when we need to just produce code that is filling in the template. So we receive the code as input in the template. We basically receive the template and we do the substitution. Why I think this is not code analysis or not code modification is because the template is not really analyzed. It's just substitution. So it's treated as an opaque from a code reasoning point of view. It's just an opaque piece of data. So we just fill in the form. This is normally called in the metaprogramming jargon quasi-quoting. That means that it's not really just a static piece of code. It's not quoted code. It's not between double quotes, but almost. It's the static piece of code doing some substitution. Here and there are markers that are replaced with parameters or expressions, more in general. And this is put positively. So those are all three data code extractor. And to manipulate the code and generate the code, we need a way to represent the code, as I said before. And the simplest form is using characters. And this means that generating, of course, is fine. For code generation, basically, or template substitution, almost any representation is fine because you don't really care about the code. It's not really code. It's just you're producing whatever without reasoning about what you're producing. And characters is fine. The problem is if you need to do any analysis. In that case, you need to interpret the characters, and it means that you need basically to write a piece of the compiler directly in your meta code. So my meta function needs to parse the string. That's really far from clear, especially if the language is topos. And another level is tokens. This is just a little bit more higher level. It's an higher level of representation compared to relatives, but there's really not much of a difference with the listener. Still, you need to do sort of parsing, and if any analysis is required. For generation, of course, perfectly fine. And another form is AST. As you probably know, AST is an acronym and stands for Abstract Syntax Tree. And it's a tree representation of the semantic of the code, the meaning of the code. And this simplifies analysis, but the other side of this is just look and the code represented as an AST can look weird. What do I mean with this? What you see on the screen now is the AST representation of the statements x equal x plus 1, where x is integer parameter in C++. I use the Sinag to output the AST. There is an option for outputting the AST. And I represented this AST as a graph for easier reading. And as you see, we have a binary operator at top level. The root is a binary operator. The next side is a reference. The right side is another binary operator, that is addition. And the left side of this addition is an implicit cast. And this is one of the problems that is often present in AST, is that the parsing can have weird transformation rules. On the source code, the left side x is absolutely identical to the right side x. But instead, at the semantic level, the right side is an implicit conversion from L value to R value. So when I think to code, I need to think this kind of stuff that can be different from the original code. And so when I'm producing, I need to produce this kind node. And when analyzing, I need to consider that I might bump into this kind of node too, even if in the source this is not pretty at present. And this is what I mean with IAM. Meta code working on the AST can be hard to correct to what was the original code, especially for if the language has a lot of hidden transformation and semantics, like for example C++ in this case has, that is conversion from a value to a value. Okay, now we are going to see how metaprogramming is implemented in a few different languages. I've chosen 5 languages that are quite similar to C++ in my view. And the 6th one is completely different because it's dynamic cutting language. And it's for the reason that in my opinion is still the gold standard for metaprogramming abilities. It's still it has still abilities that are not even in the radar of the other languages. It's still ahead. And it's also a very old language. Not many have heard about Lisp, or maybe they heard about Lisp but just in the mentioned for a very short period, but they ignored completely. It's a language that was designed in 1958. And still, in my opinion, is the best you can aim at if you're talking about metaprogramming. And we will see why. So let's start with C++. That, of course, I suppose everyone looking at this video knows about. It's a language that was created by John Strostrup as an evolution of the language C. Then we will go for the D language, that is also designed by a C++. Waterwright was the one of the early the implementer of an early one of the first C++ compilers that was Visitor Mouse. I think now is the development is has been abandoned. And while developing this language, Waterwright decided so that something he didn't like, so something he didn't like in C++ approach. So he went for its own language. And his view was also shared by another very famous person in the C++ world, that is Resco, that also helped shaping the D language with a bit. Then there is C3. C3 is much less known. It's starting to get some traction now. It's a language designed by Christopher Nelmo, and it's a lower level. I would say lower level than C++. Is another evolution from the C language in another direction. Basically, changing only what is considered to be wrong in C without adding much. Then we have Zik by Andrew Kelly, and that is quite popular now. It's still not 1.0, so it's still changing, but it's getting some traction. It's also a language that I would say a little lower layer as an abstraction level from C++, with 8 to be C++. Then we have Rust. Rust is very, very popular now. And it's also GUI, so still more stable as a language. Currently, in modern times, stable equals dead, so they don't want to be stable because then if it is something doesn't change, it doesn't react backward compatible, the backward compatibility is considered to be bad, so uninteresting. And then, as I said before, we have a Lisp that is a very, very old language, but is really powerful about metaprogramming. Okay, C++. Originally, there were only templates. So in the early version, then we got constexpr. And once The funny thing that happened is that a functional language was found to be present, and it was found by accident. It was present by accident. It was not designed to be there, because of in the type system, this language was found because there are interaction of three different uh, mechanisms. One was the overloading, the other was the recursion, and the third one is really weird. That is SFINAE. SFINAE is an acronym and means a substitution failure is not an error. And it means that if you have an error, what will be a C++ error, normally, but it's just one of a certain kind of error. So not all errors are the same. For example, missing a parenthesis is not acceptable as an error, but what was used a lot was a negative size array. You can declare an array with a negative size. This is an error, and it's normally an error, except when it happens in a very specific place of a template declaration. So not everywhere, must be in the declaration part of the template, the argument part of the template. And so if you have a certain kind of error in that declaration, then that's not really an error. Simply means that the C++ should ignore that template and not include it in the overload resolution set. So as you know, in C++, you can have a multiple function with the same name. This is called overload. And there are quite complex rules about which of the version should be chosen. And there are a precedence list, basically. And finally, basically say if you have an error when reading a template declaration, when considering a template declaration for the specific parameter substitution, if you get that kind of error, then simply ignore that template. So exclude it from the list and pick the next one in the priority. And so the trick that was used for quite a bit was declaring a negative array. And do this is an it's the default value for template parameter that is not used by the template, which just there just to make SFINAE work. So if you make compile time computation that returns a negative value, and this is very easy to do because you can have, if you have let's say a dual compilation, this is also can be interpreted as a number 0 or 1. So you can say 1 minus 2 times the compilation. This is either 1, that is valid, or minus 1, in that case is an invalid array. And if you put this in the extra parameter of the template, you basically are able to include or exclude that template depending on this. It is always for conditional. Then you have recursion. And so overload the plus finally gives condition. We go to recursion, so we can have loop, and we'll get to incomplete. And later, something more sensible was added, that was concept and if context. That is a better way to do a conditional of these two. And C++ 96 will have the introspection, and I think there is no generation inside, as far as I can tell. I saw a presentation by F. Sutter on C++ 25 conference, but I tried to feel Sutter didn't work, so maybe I did something wrong. And I think that this is still not a site. Maybe there will be something on the 29, C++ 29. And constraints on the things is something I took from presentation by Jason Turner. Let's say we need more constraints. We want constraints to be very useful for everything. And I don't agree. I don't agree at all. I don't want constraints, actually. And with this, I mean, I don't want a keyword constraint. Why I need to say that this should be computer time? Could be computer time. If it could be computer time, then I should be able to call the function without the need to mark that function as constraint. So I don't think constraints are the thing, so we shouldn't have constraints, we should just use a C++. That's my view. And And that's it. So this is a very simple of debate. It's a very stupid example, so for that. But it basically is using the if context. That is basically the compile time if done in a similar ways that is finally. And we are checking if something is integral. This is also something that simplified a bit over the years. Long ago, what that mean is integral dot value, something like that. And we are returning a string, and that depends concatenating the type with the value. And something that is important to understand is that if context, the branches that are not taken by if context are not even compiled. They are checking for the basic tokenization rules, but they don't need to be able to compile. And this was the same as finally, in case the header was giving this kind of error, this specific kind of error, the rest could contain also other errors. Of course, not errors about, like I said, missing parentheses, but certain kind of errors were out in the other part of the conflate. Okay, the language is then similar to C++. Like I said, Wilton Bright was the author of one of the early C++ compilers, and that's a better implementation, in my opinion, for the template. So still the template approach, it was the main original tool for template. For positive coding, we use template. But it's a better implementation. There are a few details on this. One important one is template mixing, in my opinion. One of the this is spoiler alert. One of the problems in C++ with template and with positive coding is that the granularity of the template is huge. A template must be the full function or the full class. I'm not take care of the template for some just a simple smaller part. It can compose different templates, and this is very useful normally. And this is just not something that is allowed. The simple class like this all in B. So this template mixing allows to take just a little function, a little declaration, a little statement, single statement, and to compose this. This statement must not be able to be compiled alone. So it's considered only for compilation when included in a context. So this is a very different approach. And it doesn't have context, with the meaning that any function is context. So you can call any function if the functions, there are limits on what you can do from per time. But if, for example, a function is pure, just manipulating input and output and non-dependency or with stuff, you can just call it on Python. So there is no context keyword. And this is actually, in my opinion, is more sensible. And the name they use is compile time function CTFE. And also it has a string mixins. String mixins, it means that you can have D function. Like I said, it doesn't need to be a close path to this function. Any D function that there are some limitations, but basically you can use all the data structure, all the code you want. In the D function that returns a string, you can put this an invocation for this function at compile time in many places, not in every place, but in many places. So where you have a type, where you have a statement, where you have a declaration at that level, you can use those string mixin. And basically what the compiler does is call this function at compile time, and the output is like replaces what was the invocation of this function. And so you can generate code that will be read by the compiler like it was present instead of the invocation. And also what you generate can be really arbitrary. You cannot just generate a single open brace, for example. So it must be as some limitation what you can do. But it's very, very general. And so you can inject the source code. You can generate a bit code. And for introspection, it uses a special API. So when you pass parameter to a CTFE function at compile time, these parameters can be also for through data, and this can be introspected using trace. This works at compile time only. If you want this at runtime, you need to generate data structure that you will access after runtime. And as a meme, I put it's just as code. It's not for fast press, not constant val, it's not recursion with binary or weird stuff. It's just a regular code. And this is an example of the very clear example. This make together is the same function, it's a regular D function. This can be called compile time. There is no perfect needed to declare. It is a string as a name, a string parameter name, and returns int space concatenated, the tilde, this concatenation, string concatenation with the name, with the parentheses, and returns underscore the name. Semicolon, close brace. And I can use it, for example, in a structure declaration to say mixin, make a getter x. And this will create a getter for the underscore x. And sorry again, this is a very, very tiny example. Doesn't really sense. I mean, the code that you say in this case is, even if they use a very little, it really doesn't add much in this case, but just think to what you can do in general. You can produce whatever you want in using the full power of the design. Okay, C3. Because that is very not as popular as this is also kind of niche language, but it has a very, very strong supporters. They have few, but they are very convinced that they're very good language. I don't know them much experience with, but they look really interesting. C3 is not the same. They are even fewer, but is getting some traction. And C3 uses still a vintage-like approach, but is, let me say a bad word, it's PHP. It's more or less like web page creation with the PHP language. So where you have your C3 code that is very similar to C, different syntax in the idea of the author is a better syntax, more logical syntax, more regular. And then you have those macros that they have a separate language for expansion. So they have template where you have loops and conditional that are marked clearly using dollar signs and hash marks and stuff. So you can see where the substitution is done and when the computation is done at compile time. And uses compile time variable expression and macro-based code generation. So there is no arbitrary code generation except for a single case that is at top level. There is the possibility to actually call an external program and include the result. So basically, it's like include mapped with key location of an external program. And like I said, it uses special macro syntax. So it's basically more or less like C, but instead of the preprocessor, it uses a Saner language. The processor is very, very weird if you ever try to do anything with it. And very little power in the processor, except a few ad hoc extensions that may added. But instead, C3 as a real language that is for compile time macro expansion. And also there is, like I said, arbitrary code generation ability, but only at top level. So that's why I put the word limited. This is by design. I have to say and don't really understand what is the reason why I can't just call for the same in the method of my non-opera scope. I mean, why the compiler cares? And this is one of the cases in which the language designer thinks that You shouldn't give this power to the users because they would abuse that power for do bad stuff. I don't like this view at all. I am more for freedom and education to avoid bad use. But this is what the C3 language does. So I use this name to say that, okay, no preprocessor, let's use macros. This is a very skill platform. It's not a version of one. Once again, sorry, but I need to just use one slide. And here we see a macro. That is the definition instead of define. The keyword is macro. Void, logif, enable. So basically, this is uses the @ sign for the macros, not a declaration, any invocation. So you cannot confuse a macro invocation with a function invocation. So this is pretty remarkable. Differently from, for example, the C preprocessor. This is one of the mistakes of the C preprocessor, depending on the outlook. And here, the dollar if is a conditional compile time. So it's marked with a dollar. And this is a parameter. This dollar enable means that it must be a compile time constant, a compiled time known value. In this case, is a true value. And this part is what is expanded. So basically, we are seeing a template, but it's included only if enable true. Otherwise, it's just empty. So this function is going to have an empty body. And that's it. There are a few, I think, I can conclude with another of the languages, but the braces, you see them, they are present, but they are not really there in the expansion. So they will be just a single line in case of expansion without the brace. I hope I got this right and not making confusion with another language. Sorry if this is the case. Okay, Zig. Zig is very popular, and it has this concept of conc time. And this conc time word means that compile time execution. Templates are basic, very, very, very simple. You look at them, they look like normal C declaration or C functions. So for the function, they look like normal C functions, except that some parameters are marked as comp time, and those are basically templates that can be expanded if needed by when called with types, like parameters. The language is identical to Zig. The semantic is very, very close to Zig, so it's almost Zig for the language. There are key differences, but this contain allows for very arbitrary computation at compile time in Zig. And introspection, like in C3, like in D, is done using a special API. If I'm not mistaken, it's still something that is stabilizing, so they're changing a little bit the API, so you can introspect the code. And for now, if I understood correctly, it's just for structures. So you can introspect a type, but you cannot introspect a function. So it's not looking inside the real code, only inside the structure declaration for introspection. And generation is also only about structure. You can generate types at compile time, and new types are declared compile times. So you can generate arbitrary, so not only template based. You can build a type from scratch compile time, but you cannot build code from scratch. And if I understood correctly, this is not was tried for a mistake or a language and design choice. And yes, or maybe we change it, but I just say that the is still in flux state. Flux. And like I said, there's no way to create consistency, so only the construction. And so it compiles the regular code, always a spin. This is an example, quite a bit more convoluted than other example, more sophisticated. And this maybe makes even sense at this very center. I'm creating a C function that, as you see, accepts a compile type parameter. So this is made to be called a compile. Well, the two compile type parameters. One is the type, one is the dimension of the vector, and this creates a type. As you see, right here, this is the result, the return value type of this function is a type. And as you see, we have return struct. So we are returning a type. And in this type, we use degree substitution basically. So we have the t, the n. And at sign this is a click that we be able to refer to a type inside the type, even when the type has not yet a name. So this has no name, so you can, with this, you get refers to the same type. And this is a loop that implements addition, element by element addition. This is the standard way to make a loop in Zing. So it's not special syntax, and clears the invocation. As you see, here we are not marking this as in any special way. So, for example, let's first see what to keep the usage of this kind of macros, basically completion of the completion time and functions, marked the same as the regular code. And then we get the Rust. In our list, it's the last of the C++-like languages, so it's not tighter than other calculators, it's similar to C++. Rust has basically two different engines. One is the relative macros. That is macro roles is the syntax for this. And they are basically templates with the addition of a pattern matching at the beginning. So instead of having a template to have in C++, you will do several templates using overload. In Rust, they use instead these macro rules with dispatching using pattern matching. And there is a DSL, like in C3, you have a different language for expressing the expansion, controlling the expansion with algorithms using conditional and loops. And then it has a separate tool that is a const function for total head duplication. So if you need a unique duplication, instead of a complete installation, you have a const function that is like a const text, more or less like const text. I think it's very, very independent what it can do. Go on text frankly. Yeah, if I'm not mistaken, Rust is also changing with the times, so maybe it's something that was related to in related time and the evolution of the language. You refer to when I read the documentation. Oh, okay. Maybe I forgot this very important point. I don't have any real world experience with those languages. I just read the documentation, maybe applied a bit in the playground, or it's for little just tried a few examples, but I don't have any real experience in those languages. So you should take what I say with a grain of salt, because maybe I'm saying something wrong. If I do, please let me know, because this is something I really care about. If I said anything wrong, anything factually wrong. And this is also the gradient macro const function with compiled and computation and procedural macros. This is a completely different list. And it's the of all the languages we've seen so far, it's the only language Rust in which metaprogramming is done using the real Rust language. Because the procedural macros are real Rust code, normal Rust code, non-imitational code. The only thing that you have to say is you have to inform the compiler that a certain crate contains procedural macros. My guess is that this is because those crates need to be compiled first, because you can then use those crates directly at compile time. So just knowing the interface is not enough. The compiler has to invoke your Rust code at compile time, and so that crate must be compiled first. So declaring which crate contains procedural macros is important, and also the dependency of the interfaces forces the order of compilation of this procedural macro. If a crate with a procedural macro uses another crate with procedural macro, there is a topological dependency. I think that, I don't know how, but I suppose that probably loops are not committed in this case, so dependency loop are not allowed. But for example, I don't know if dependency loop are allowed or not in regular crate. There is no any technical limitation for this, for blocking this. But like, modular question, there is no problem if you just need to know the declaration. But for macros, of course, you need, because those macros are invoked at compile time. And the procedural macro just takes a stream of tokens as input, then it also a stream of token result. So it uses tokens, so not characters, but it's absolutely general. In addition to this, there is a predefined crate, a standard crate that is part of the library that is named the SYN, SYN, and that is able to pass a stream of token into an AST representation. So your procedural macro can use the AST representation, and it's also able to take the AST representation back to a stream token for generation. Something weird, in my opinion, is that this SYN crate is not internally used by the compiler. So it's a different implementation. And I don't know the technical reason for this. In my opinion, that's kind of weird. Another thing that is weird is that Rust has many different macros in the language, as part of the language. For example, you have for formatting, you have different macros that are available when you use Rust, but they are not implemented using the Rust system for macros. So there are many built-in macros that are not built in Rust. They are not procedural macros. I don't know also if this because it's technically possible to do, or just difficult, or just not convenient. But that's something that is kind of weird to my eyes. One thing that also is done by Rust, and as far as so Rust only, of the language we already saw, is that there is the agent is implemented automatically. What is agent? Agent is when you have a metacode that injects code. This code can inject variables, names, and you must be careful of not stepping over variable or names or type names or function names of the user. So if you define your local function, but then you expand part of the user code, but this code uses a function with the same name, but was a different one, was a function from the user, you bump into a problem, because you are either the user code calls your function, or your code is calling the user function instead of your own. And this problem is called the hygiene problem, and is something that the Rust macros are handling automatically. And this is the slide. So we have a constant function that's very limited. You can do some computation. Then you have macro rules, that is the greatest function with us to separate the language, the for function. And then you have top factor, that is the most powerful tool. And this is a very simple example of macro rules. So we have a create function macro that takes as only parameter identifier. This is the pattern matching happening. So if the argument to create function is an identifier, then this expansion is taken care of. If none of the expansion take care, you get a compile error. So at least one must match. And you can have a recursion here. So you can expand to use a create function A. Not it is in this case, but it's something that is possible. And here you see the expansion that uses FA to refer the standard parameter, and it's just expanding to another macro that is a predefined macro that is print, and basically knows out this print code. As you see, we have a identifier that is another macro that given the identifier goes to a literal identifier. This is a predefined macro, and so what you get is a println that is storing with a format string and a string literal. Okay, there is a mistake here because when you invoke a macro, you must use an extracted mark. So it's Rust makes a clear distinction between function invocation and macro invocation. Also, so this is my typo here, and you get this notification. Basically, we'll expand in a println with a format and a string, and as far as Gemini told me, these won't be expanded in a single literal. So the println macro is not smart enough to include the directly literals passed as a substitution point in the braid of the format thing. But we can do that explicitly if instead of using this expansion that is expanding to a regular println, we do a different expansion. So we call concatenation, that is another compile time macro that is available in Rust, predefined macro that can concatenate strings. And we get the same. And okay, this is the Rust example. Now we have Lisp. For Lisp, Lisp is a very different language from all the others we saw. It's by default dynamically typed language. You can declare types, but by default is like Python, to say something similar. And one big difference is that the source code in Lisp is not string counted, but is already a data structure. So Lisp code is data by definition. It's not something that you can represent code as data, and as code is actually data. So the to the compiler is a data structure, it's not a string character. There is a separate path before that translate characters into the data structure, but this can be used also for data, not for code. And metacode is a regular Lisp code. Like in Rust, there is not a subset, not a different image, you do whatever you want. And there is quasi-polling, but just an helper, just a syntax simplifier. And one difference between Rust and Lisp is that in Lisp, quite a bit in all the system I look at it, and also in the ones I implement myself, most of Lisp is written in Lisp itself. So you have a very basic Lisp system. Anything else is built in Lisp using Lisp macros. It's not predefined the compiler. So the compiler doesn't need any special case. So it's very, very simple. This is something that is usually varies now I will explain more detail. And metacode normally works by lowering. So you basically create a macro like if you use this higher level concept, and this macro basically translate this higher level concept in the concept without the macro. So what would be the same expression in a Lisp that didn't have that macro? So this is what is lowering. And so there are no many macros that predefined that do magic. There is no magic in Lisp. Basically, we have a very basic, very basic kernel, very limited, minimal kernel, and then everything else is done by lowering. This is very common in Lisp. And I put in this slide. I've put in this slide because it's really it's not something that I can be said in 10 minutes. But if you really take some time looking at the Lisp ability in metaprogramming, I'm talking about the ability of metaprogramming. It's really on another class. It's something completely different. Okay, now we have this table that represents all the languages I've talked about in this presentation. So we have a C++ that has quasi-quoting, but not a really nice form of quasi-quoting. There are a few slides now. And computation that is not really nice as computation. Like I said, you have to mark what is user, your many limitations. They are being removed as type passes, but I still remember. Like it was yesterday, but it was probably 15 years ago or something, at a Lisp conference, was a C++ 11, uh, was the new thing at the time. And they had Constexp. The very early version of Constexp was very, very limited. And I remember saying at someone at the conference that I wanted a Constexp open. And I can still remember the eyes, these bug eyes they gave me, and they were close to call the police for get me escorted out of the conference for saying such a, which is such a bad thing. I mean, I wanted to open, but I'm crazy or whatever, or just to take me out. And it's funny to say that now every 2 years they are something, and probably in another 20 years we will get those tries open. Because there is no reason for not having it, and Constexp open. And well, the right now is still limited. There are a few limitations about what you can do with Constexp function for no real reasons, in my opinion. And like no code generation, no code analysis, and no code transformation. Code analysis will be in 26. Apparently, for structure only, like all the other languages we're going to see in the section of Rust, that also can introspect functions. And code transformation, of course, not. And then we have the language that has much better possibility, in my opinion, and much better computation abilities. Code generation is the full power because you have string mixing, so you can generate anything you want to generate. And code analysis using APIs. And code transformation is not possible because introspection is only allowed for only for structure. So the code transformation means functional code transformation. This is not functional analysis. And then we have Secret. That is nice possibility, little better possibility. The computation is nicer. Code generation is so, in my opinion. And code analysis is also, this is my impression. I don't have much experience, so maybe please don't take this as too much of opinion. Is opinion is not based on no experience, so it's just the first explanation. And then we have Zik, that also considering that's okay. Computation is good, because we have compiling you can do. Code generation is not allowed by design, so this is a choice. And code analysis is better API than C3, in my opinion, comparable to D. And code operation not because you can generate code, so you cannot transform code. You can generate you can generate structures. That's okay. And then you have Rust. Rust is good quasi-quoting with different with the pattern matching. I would say I don't know cost function are limited, but it's kind of okay for competition. You have code generation for capability with proc macros. You have decent code analysis, and actually you can also introspect function because you have procedural macros can read anything, and using the sync rate, you can use AST, and so you have full metaprogramming power with some limitation. The map could be file first, the scoping, things like that. A code transformation is possible, and then you have Lisp, that is really another thing. Now I have a few slides on Lisp. I didn't done here because I guess it's, like you said, very different from all the other languages. So if you know C++, that is my supposition, if you're watching this video, then reading the other languages will be pretty natural, and they will look not too weird. They're very similar. Lisp instead is very different. So first thing is homogeneity. That means that the like I said, the Lisp source code is a Lisp data structure, and coding data that is code is digital. This is the thing. It's not a view. Is not. It's just what it is. And meta code is just regular code. So you have just this function. And there is no runtime complete time distinction. Almost. The example we will use are from Common Lisp. Common Lisp has some limitation for reasons that the process explain now. But basically, you know if it's compile time or runtime. There is this distinction is in some form present, but is really tiny compared to other languages. And this is not something that must be present in the Lisp system. I implemented the Lisp system which compile time is just not a word. I mean, there is no compile time. It's just runtime. And because compilation is a runtime function call. I call the compiler passing a data structure for the input, and I get executable code. So it's just a library function. The compiler is just a library function. This is possible to do. It's not what the common Lisp system does for compilation, but it's not something that is impossible to achieve in this. And this is an example of the syntax. I understand that can look weird compared to other languages, but it's very, very simple. So we have list is elements separated by spaces and enclosed in open parentheses. In parentheses. So there is no comma for separating elements, so we don't have the three common problem of JSON, something like stupid like that. And we have one concept that is present in Lisp is that the elements can be strings, they can be numbers, but they can also be symbols. Symbol is a name. It's like a string, but it's not a character, it's just an identifier, a keyword, or a name, okay? So here we have a list. This is a list that starts with the symbol define, that stands for definition function, define function. Then we have the function name, that is another symbol, that is Fibo for Fibonacci function. And then we have a list that is the list of the parameters. Here we have just one parameter that is n, that is a number. Like I said, the list is, you can think to it like Python, so dynamic piping. So we know that's a number, but it's not stated here. You can state this. You can say in common Lisp, okay, I know this is a number, must be a number. So you get both compile time errors, and you can get compile values, actually. You can get either runtime errors or optimization for speed if you assume it's will not check if you want to go fast. And then we have a conditional that is a list starting with a if. And here we have a function call. A list has no operators, no precedence, no associativity, because there are no operations, just function. So this is a function named less than. That's a valid name for a function. So we're comparing n with 2. The other parts are the arguments. So I compare n with 2. This is the case when it's true. The value must be 1. And this is the case when it's false. That is another function call. The function is named plus. And the elements are other function calls. I'm calling Fibo, that as you see is the same name of the function I'm defining. So this is a recursive function. This is the naive implementation of Fibonacci function in Lisp. I want a conditional. Conditional is an if, is a list with 3 or 4 elements. The first one is if, it's a keyword, let's say. Then we have the test, that will be an expression, can be a variable name, but can also be another list with more complex stuff. another expression that is the value is true, and optionally if the value is false. This is not a function call. This is basically the AST node for conditional. That you have three. It's an AST where we have either 3 or 4 elements, actually 2 or 3 child, let's say, elements in the AST node, and it was like in other languages. Okay, one part of that is very common in Lisp, but also in other languages, is when you have a conditional and without the else part, only the true part is present, so the false part is nothing. But that part is composed by several steps. Oh, by the way, Lisp is not a functional language. You can find this on the internet, but it's just a false thing. I mean, if Lisp is functional, then also Python is functional, because it's very, very, very similar to Python by default. It's very, very similar to Python, if we exclude the metaprogramming abilities. And so not functional. So statement can have everything is an expression, different from Python, but you can have send effects, so it's not a function like in any, not purely functional at all. So you can have multiple. Makes sense to have multiple expressions one after another, and the value is the value of the last one. This is what paren is, and more or less like open brace in C is a block in the C or C++ language. And so you have a test, and you only have a body composed of several elements. This is a very common use. It's so common that Lisp provides a dedicated syntax file for this, that is named the when. The when conditional takes a test and then just all the other elements of the body. So you get one level less, so you don't need to open a brace, basically. And one important thing is that if when was not present in Common Lisp, it's already present in Common Lisp, but if was not there, it would be very easy to add, because this macro definition is what is implementing when in Common Lisp in a Lisp that does not have this function, this syntax construct. And how it works, basically, instead of saying the fun, I say def macro. That macro means it's just a regular function, but the compiler is informed that this function should be called at compile time. In Lisp, the macro invocation is not marked in the syntax. So when you see a list where the first element is a symbol, that may be a macro invocation or a function invocation. You don't know looking at the calling side. So you decide if it's a macro or not at the definition side. So I define when to be a macro, and the only difference is that this is a regular list code with all the abilities of the regular list code, but will be invoked when the macro, when some code is using the macro at compile time, not at runtime. And it's named when, so this is the name of the this macro. We receive a test. This won't be the value of the expression, but will be the expression itself. So basically, a macro receives the source code of the parameters, not the actual value of the parameters. That will be known only at the runtime. But the source code is known at compile time, and this is what is passed to when. That is a macro. And the rest is it's a variadic function with all the other arguments are collected in a single parameter named body. And this body is a list of expressions. So, and this is the implementation. It's an invocation of the list function. It's a regular function in the list that creates a list of the elements, like in Python. And the first is quote if. That means it's not a variable. I need the word if as is. This is quoting. The single quote before is just means the rest expression as is without evaluation. So the value would be if, the symbol if. Then we need the test, that this is the algorithm we got passed. And the third element would be a concatenation of a list containing the keyword progna and all the values. So it will be a list that starts with progna, and I will have all the other expression. And basically, what it does, this function, is translate when test into if test program expression. Because the compiler C1 calls the macro, this macro we saw before, passing test expression and this in the list body. And then the expansion with the list starting with if, the test, a list starting with program, and all the other elements concatenated to the same list. So this is the expansion. Macro expansion is the technical term that's needed in the list jargon. And but something important to understand is that this is just a regular list code. It's not a grade. It's just code. And if written in Python, this will be more or less like the same code that it's the implementation was in Python, but was in I think this code. Sorry for this weird, but this is probably easy to understand for most Python. So basically, it's a function that takes test and arbitrary number of elements after, and then returns a list. Let's start with a keyword, the test, and the concatenation of a list with just a keyword with all the elements. So this is the practical implementation of this macro, so to say. One important thing is that so list doesn't have quasi-quoting, doesn't have template, it has templates, and this code is actually equivalent to this code. This is much shorter. But this is not a special case. This is something I can use in any list program, not only in macros, and it's just a list creation utility. So the back quote means this is a quasi-quoting, that's the name. And is whenever is just a template, and the comma is where the substitution is going to happen. It's more or less like the back quote in JavaScript, when you put in strings, no, and the comma is equivalent to the dollar open brace in JavaScript, JavaScript phrase. And so we have this comma that means, okay, this is, you need to pay, the next is an expression is not literal. And this is a different expression, this is a different way to refer to an expansion that is called splicing. The expression must be a list, and instead of replacing the list itself, we put the element of the list. So basically, this allows me to do the concatenation in the template without having to write in the space. An important point, wrote test and model when I use comma or comma splice. Here I'm using just a parameter name, but I can use whatever I want. So including an expression. I can use a comma, open parenthesis, then will be a list expression doing computation. So this is fast expression, like in JavaScript, is the expression, not like in C++, where it must be a parameter, because it's not back, it's just the name of the template parameter substituted. Only the substitution was for parameters. And okay, back to the C++ metaprogramming, and here I'm gonna say why I put some tiers on the table, and why I think that C++ metaprogramming has problem. There is something wrong. I said grammar. Basically, C++ metaprogramming what provides for what have the metaprogramming abilities of C++. They are the constitution that is named the quasi-quoting, and is the most trivial example of metaprogramming. Better implement, and that's it. That's what C++ provides for the metaprogramming. For metaprogramming, only template, substitution, and better implementation only. And almost because now they are adding something, so we got contextual, that is okay, better than using template expansion to do computation. And they are now we will get We don't have yet, but we will get, for example, introspection, some limited form of introspection, not consideration, nothing fancy, but something with it. And just to give you an idea how bad the situation is, we only got strings. I'm not talking about the with stuff. I mean, just being able to use the strings at compile time, just a few days ago. This is not something that it took many years for C++ to get strings. That's not how bad it is. And the best attribution, I mean, bad independent, and why? First of all, the substitution points are not really in the market. So when I say the same word X in an employee, is this literal or is this substituted? Who knows? Go check the template parameter list. Also with some weird rules. For example, you normally can open brace and declare a variable named X in C++. But this maybe is not valid in a template, because if X is a parameter, you are forbidden from shadowing. No idea why, but this is what the rules are. Maybe there are technical reasons. I know, it's kind of weird. And all this wouldn't be disappeared by just using a single character to mark the substitution point. Would be easier for the readers, easier for when you write the code. But no, it's just using it's not clearly marked for reasons, like I'm going to say. Another big issue is that this is a bigger issue, is that template must be the full function of the full structure. There is no partiality possible. This is very annoying. You are forced to use utility classes just to get something. You have a template for your reuse. A template is another template. You have to make a different class because the template must be the whole thing. They are not the template mixing, for example, of D that allow for single chunks to be used as template. And the substitute can be an expression, but only a parameter. And this means that if you want to do any computation, you must use an utility class to do the computation. And this was very common long ago. Now with context, you can do some computation per time. But still, you need to do a separate context fraction to do the computation. Because when you use, let's say, two template parameters A and B, and in your template body you write A plus B, that computation is not done during the template expansion. What happens is that A and B will be substituted, then the compiler will normally use a constant expression for the constant folding for the computation. But it's not done during the expansion, so you cannot use an expression, let's say a conditional or whatever. You must declare a separate template just to do the conditional. I cannot say, here I want this or this stuff or this other stuff. You must use a different template just for doing that. And simple button computation is something that don't happen by accident originally. So it was discovered that it was possible to do the computation because of three element checks. Like I said, there's overloadings, finite, and recursion. And all three actually gives you this triplet gives you two incomplete language. And code is code to completeness. Means that you can compute anything that can be computed. So really you can do any computation. But data complete means that any computation can be implemented using C++ template. But it doesn't mean that if you have a Turing complete language that you should do the computation in a Turing complete language. For example, there are many languages that are Turing complete, but they are absolutely highly used as a programming language. Even a game of life, with the cells and the evolution thing, that's Turing complete. You can build a computer using Game of Life. You can look on YouTube for videos where Game of Life is implemented in Game of Life. And another separate we often do is the language brain factor. This is not a bad word, it's the name of the language. And it's Turing complete. It's only defined by 8 characters. For example, even the number 14 is difficult to implement. A program that does 14 in BrainFuck is not real because you don't have numerical literals. You have to start from one and increment until 14 to get the number 14. But it's totally complete. You can find translators from C to BrainFuck. And but doesn't mean that we should call him BrainFuck. It's very complete, can implement anything. So we should call him BrainFuck. And my opinion, the answer is, of course, no. If you want to play, that's fine. That can be even interesting as an exercise, like walking on your hands. That's nice. But do you want BrainFuck called in production? You want to maintain BrainFuck code? Of course not. It's highly, it's nonsense. And so, C++ was discovered to have this kind of incomplete sort of language that you have to use straightening and recursion just to do iteration or conditionals. And but this I think that the discovery damaged the C++ seriously because any way to create things prevent C++ from getting a real metaprogramming solution for anything that's not legal for more than 20 years. And so having this ability was what, in my opinion, slowed down decent C++ progress for the metaprogramming side. And even if this waste was terrible, and so this term was really barely usable. In the origin, the compilers were getting internal errors or exploding all the time when you were using this kind of metaprogramming abilities. Why? Because the designer of the compiler thought that you just wanted to do address substitution, not computation using recursion. So they were, after 3 errors of recursion, the compiler would explode. And today it still is absolutely complex to write templates. It's even the users of the template for the writing. It's even the compilers. We can get code that takes forever to compile, and still today it's impossible to do that. So I just say code compile time computation is just computation. I want to do this. The band, for example, I want to, under my prints, I want to stack it to be the market. And this is still, there is maybe when it's split one case, there's still something possible. You just run the code, whatever. The error message, when you make a mistake in a template expression, are literally a joke. I remember when I started working for the current company, there was a colleague that was using a plugin from a company. The only reason for the plugin to exist, the only capability of the plugin was debugging the print errors for Visual C++. And that plugin was the only, if I remember correctly, was the only tool sold by the company. So the idea that you can have a company, business, it is only deciphering error messages, in my opinion, is telling you a lot about how bad those error messages are. And this is still today there on the same. Now, concept in theory, they should simplify. My experience is from now, I still get 20 screen of error messages because I forgot a cost. And really garbage. It's very difficult to find where is my mistake when using this stuff. And this stuff is so bad that it's really like a joke. I mean, it's difficult to make the salary how many it is. It's so bad that it's not possible to salary. And it is still today. So this is very, very horrible. But you can do stuff with this stuff, and this can represent in a nicer way, in my opinion. And there are a few big issues with the code. For example, metacode is complex by itself. There is an essential complexity in metacode because the code, what metacode manipulates, is complex. It's not an array of numbers. It's something that is recursive in nature, is as a reference into really complicated stuff. So the metacode, code that manipulates this stuff, cannot be trivial. But much of the complexity comes from in C++ comes from the how bad the syntax it is and the semantic it is. How the most complex code is, the most complex metacode manipulated is in even worse form. So if code is complex n, the metacode for manipulating that code is complex n squared, because and the way it was to metaprogramming, because you are manipulating something that is really complex. And C++ complexity, the syntax and semantic of C++ is really, really, really complex. And another thing that the static typing, that is fundamental idea in C++, that doesn't really work well with metacode. This is something that has been also partly, this is my personal opinion, I wrote a lot of pilots and stuff on metacode, and this is something that I got from, I found myself, but apparently the people in the committee agree, because C++ 26 will have introspection, but the key element of the introspection, that is this info object, so to speak, is actually dynamically typed. So it's just for one type or for all the stuff you can represent. And this works much better than static typing. C++ is about static typing, but metacode doesn't work well with static typing. It's easy to write, much easier to write dynamic typed metacode. And we also list of factors is compile time, runtime, speed of sessions. And I don't know why. There is this idea in working, it is user code executed, that's a runtime. If it problems with computation, yes, it's a runtime. It's called user code executing. And but the simple is fact that there must be a clear distinction. I don't understand why. This is so obsessive about separating compiling from runtime. And also metacode is about function bodies. This is something that is not even in the radar. I didn't see anything even talking about this. This is some idea that is really, really, really far, if further we get to C++. Why I think there is no hope? That's kind of situation where why I think there is no hope for C++. Every 3 years, the artificial complexity of the language increases. So we get more syntax, more semantic. And every increase will make metaprogramming harder, because the language becomes more complex. Especially because it's not a complexity that is automatically reduced. There is no lowering idea. There is more built-in complexity that is not expressed in the previously existing concept. And the syntax gets more complex, of course. And semantic and syntax get more complex. Also, we get more ad hoc solution, built-in solution. For example, in my opinion, we get contracts, for example, that I think they are completely unneeded. I mean, I can implement contracts. Right now, it's very, very easy to implement a contract using some bad tricks. If you want to release some contract macros, some abilities that is implemented in already what is already so if you want to define a standard library for contracts, that's fine, in my opinion, but another ad hoc syntax, another syntax twist just to have contracts, in my opinion, is totally unneeded. It's actually damaging C++. And this is not you and I error, it's something that is happening today. They added totally yesterday. And so this is, I don't see this is gonna slow down. The addition of bad stuff like contrast is not very absolute. It's better that they add it to the language. Why do you need to add this to the language? Add it to the library. Make a library for contracts if you really think that this is the best thing in the universe. And the compile time and time speed is still considered absolutely broken to understand the importance of the compile time. This is totally nonsense. And all this, there is still no code optimization side. And this is what makes me think that programming, simple programming is packed up beyond any other. So there is no way this is going to be fixed. but I need it like monthly. Please remember that I know. So maybe this is just my part that is yelling of the new stuff. I have seen this is bad because it's new. And that's it. So the presentation is over, and please remember that like I said, I experimented a bit with automated, studied a bit of language, implemented many of them, but in this example, I'm talking about 6 languages, and most of the presentation is from reading the documentation. So if I made any mistake, please let me know, and don't take my word for granted. Read about other languages. Something that kind of confuses me is that there are people that say, oh, metaprogramming is absolutely great in C++, you can do amazing things, but they didn't see any other language. They like saying, oh, this restaurant is absolutely fabulous. Did you try any other one? No. How you can say that's fabulous? And so please go around and check out the languages. The documentation may be right a little broader than that, just to get a taste of what others can do before saying that C++ is amazing. And please also be careful about the later metaprogramming C++ that can be a challenge. And if you're smart, your brain likes challenges. But please remember if the challenge is real or not. For example, in the early C++ day, even making a loop was not trivial. And people was getting this dopamine shot from, oh, I was able to implement this stuff that, uses the custom to make a loop. But please remember that this limitation, the C++ debate with programming cannot do loops, could do loops, you have context loop, but in the beginning, it was just you had to do recursion and spinning and that stuff. This limitation is not real. It was a circle decided that then you don't have to make loops. You have to use recursion. So when you overcome this limitation, you didn't accomplish anything. You just get over an obstacle that was invented. It was not something real. You're not solving a real problem. You're just solving a puzzle, a pointless puzzle. You are coding a reward in breakback. After you release that, you didn't accomplish anything real. You just got over a stupid limitation that is part of the problem. You solved the puzzle. And but this can be problematic because if you're smart, you can be sucked in into writing contained the code. And why I'm saying this? Because I've been there. I wrote meta code that now I have regrets about because that's in the passion and it's a bad idea. And I maybe my metacode was not really useful, but when you write it, you get the impression like you did something. That impression is false. You just got over arbitrary limitation. You didn't solve the real problems, but you blocked the knowledge. It's basically nerves 90, if you know what I mean. Okay, that's really all. Thank you for watching, and see you next time. This is sorry. Sorry. Okay. Okay.